In this video, we're going to look at a theory called the valence shell electron pair repulsion theory, or VSEPR for short. What this theory allows us to do is predict the 3D molecular structure of a compound or molecule, approximating bond angles around what we now call a central atom. What we're going to use in order to determine or predict this 3D molecular structure around that center atoms are the number of bonds and lone pairs attached to that center atom. And we're going to assume some things about that center, those bonds and lone pairs. And we're going to assume that their arrangement around that center atom minimizes what we call repulsion. So in order for them to minimize repulsion, they're going to have to be as far away from each other as possible in angle. And so there are 5 different spatial arrangements that we're going to study in this class that will predict what we call the electron pair geometry. Now keep in mind an electron pair can either be a bond or a lone pair. The first particular arrangement is only if there are 2 total regions of high electron density or bonds and lone pairs. That's another term for that. And this particular arrangement is where they're as far away as possible by still being attached to the center atom, and they give you a linear arrangement. So you'll have one area of high electron density and another area of high electron density, and they're as far away as possible from one another to give you 180 degrees. The second kind is one where you have 3 regions of high electron density areas, bonds and lone pairs, and the arrangement that they're going to take is something that we call trigonal planar. They're all in the same plane. They are as far away as possible by still being attached to the center atom, and in that process they'll have a 180-degree angle between each region of high electron density. The third particular type of spatial arrangement is one where you have 4 regions of high electron density. In that arrangement, you're going to get something that looks kind of like a pyramid almost. We name this tetrahedral, and that tetrahedral will have those 4 areas where one is pointed in the z-axis, like so, and then you will have 3 others pointed down at 109.5 angle from that z-axis. And also, even the angle between these are also 109.5 degrees. So every particular area of high electron density is at an angle from the other areas of high electron density at 109.5. The fourth type of spatial arrangement has 5 regions of high electron density, and we call that trigonal bipyramidal. And trigonal bipyramidal, trigonal meaning that you're going to have a kind of like a 3-sided pyramid almost here, and then you'll have 2 of them because you have one on the bottom as well. Depending on the particular items in question, the particular areas of high electron density in question, you may have different angles. So if you have the area of high electron density on the z-axis versus anything on the x or y-axis, that angle is going to be a 90-degree angle. However, if you're going to compare anything within that trigonal plane here from one another, that angle is going to be 120 degrees. The last spatial arrangement is something that will have 6 different regions of high electron density. We call this particular spatial arrangement octahedral. And octahedral, from every spatial or area of high electron density no matter where, anything adjacent to that, rather, will be at an angle of 90 degrees. So these are the 5 possible electron pair geometries that you could potentially get in spatial arrangement that the VSEPR theory helps us predict. So let's look at something that we want to look at, the electron pair geometry, versus something that we have used this phrase quite often called the molecular structure. Well, the electron pair geometry predicts bonds and lone pair placement or arrangement within a structure. The molecular structure is actually what the molecule looks like, only taken into account bonds to other atoms. And you won't see the placement of a lone pair yet. Its repulsion effect will still be visible. And so sometimes we see this molecular structure called molecular geometry. And ultimately, the molecular geometry is what we want to know about a substance because that will help us predict things like polarity and such. In order to determine the molecular geometry of a substance, we can use a chart like you see here. What you have here is a chart that has the number of areas of high electron density in the first column, and in the second column, the associated electron pair geometry. So for instance, if you had to happen to have a substance that has 2 areas of high electron density, the electron pair geometry of that is considered linear. And you cannot have a substance that has 2 areas of high electron density and one of those being lone pair. They're always going to be a bond that goes to another atom. So you'll see something here. There will be no lone pairs, and the molecular geometry of that substance will always also be linear. However, say if you have 3 areas of high electron density, the associated electron pair geometry is trigonal planar. If none of those areas of high electron density are lone pairs, then the trigonal planar structure will still be the molecular geometry. However, if one of them is a lone pair, like you see here, then the molecule itself, if we were to kind of take the lone pair away and make that not visible, the molecule would still have a bond angle between these 2 bonds. That's an angle of 120 degrees. The electron pair still repulses. It still causes the effect of having the trigonal planar shape. You just won't be able to see it. And so this particular chart will guide you through determining what's the molecular geometry of a substance based on the number of areas of high electron density and the number of lone pairs. So let's go through the process of using the VSEPR theory and ultimately determining the molecular geometry of a structure. So the first thing that you're going to do is draw the Lewis structure of a molecule or polyatomic ion. Then what we're going to do is we're going to determine the number of areas of high electron density. That'll help us identify the electron pair geometry. And then once we have that electron pair geometry identified, we can look at the number of lone pairs. That will tell us the molecular geometry of this structure. So let's try this by looking at an example problem. So let's go through and try to figure out what the electron pair geometry and the molecular structure or molecular geometry is of this compound NH3, which is ammonia. So I went ahead and did the NASA table for you, and I have calculated there to be 3 bonding pairs and 1 lone pair for this structure, and I've drawn the associated Lewis dot structure down here. So this is the 2D Lewis dot structure. The only thing that the Lewis dot structure actually tells you is what is attached to what. So it does not tell me anything about the 3D spatial geometry. That is where your VSEPR theory comes into play for looking at your Lewis dot structure and then associating something in 3D to that. So what we do is we're going to figure out how many areas of high electron density that are in this structure, and that is going to include bonds and lone pairs. So we're going to highlight them. Here's a single bond, single bond, single bond, lone pair attached, and we're always referring to what is attached to the center atom. So this now we know that that value is 4, okay? And so if we know that there are 4 areas of high electron density, we'll go back up to our chart here, then the associated electron pair geometry with that is tetrahedral. And so we know that that name is tetrahedral. And for you guys, all I'm going to require is that you be able to tell me the name. If you want to get super fancy, you can try and draw it. And I will tell you that we tend to draw lone pairs in the kind of like 2 dots and a little bubble that you might do there. We would draw kind of a plane of a bond that's in the plane of your paper, like a solid line like you see here. If something is coming out towards you, we use a wedge like that. And if something is going behind the plane of the paper, we use these little dash lines as such. And so this might be how you draw the structure of NH3 in 3D, if you could, of the electron pair geometry. And then what we're going to do is we're going to look at that and we're going to go, hey, how many of the areas of high electron density out of the 4 were lone pairs? And it turns out it was 1. So we know we have 1 lone pair. So let's go back up to that diagram again. And so now we go to the molecular geometry columns and we find the number of lone pairs. So ours is 1. And so what we're going to do is we're going to follow that down and match with the row of the areas of high electron density. It turns out that the structure, the molecular geometry structure, is going to look something like that. And that's kind of sort of what I've drawn that you kind of see here. But what we're going to see, what I want to show you is when we draw the molecular geometry of that structure, we draw it using the same angles of all of the bonds to our atoms that are present. However, we don't draw the lone pair because you don't actually see the lone pair in the atom. You just see the repulsion that it does. We are only interested in the actual bond angles of bonds from atom to atom. And so there is actually a name that's associated with something that was tetrahedral in electron pair geometry and has 1 lone pair. And if we'll go back up to that chart one more time, I kind of skipped over it. It's called trigonal pyramidal. So that's the name, trigonal pyramidal, of the molecular structure for this compound. So that's how I want you to use the VSEPR theory and how I want you to actually identify the full-on 3D structure of that molecule. Let's try this one more time. Actually, before we do this, I wanted to show you that there's a program that we can use to actually model these in 3D that makes it a little bit easier to see rather than looking at my drawings. And it's one that's called Phet Simulations. And Phet Simulations is something that you can download on a smart device or you can use on your computer. If you just type in Phet, P-H-E-T, simulations, and it'll go to the molecule shapes program, and this will allow you to model molecules that have a certain number of areas of high electron density. So this is actually a model of NH3, where you have 3 hydrogens and 1 lone pair. And the electronic geometry is down here is called tetrahedral. The molecular geometry is trigonal pyramidal. And we can actually show all the bond angles. Bond angles 109.5 is the angle that's predicted for tetrahedral. And we can actually show this without the lone pair present. So you can see that this would be the 3D molecular structure of that substance. All right, so let's go to another example. And this is our second example, and we're going to do CLF3. And this one, I started the NASA table, and I calculated a couple of things that are a little different than what we've seen before. One thing is that when I calculated this to have 2 bonding pairs and 12 lone pairs. And when I started to build the skeletal structure that you can kind of see down here, you can tell I have to have at least 3 bonding pairs. So we have seen that part before, where if we don't have enough bonding pairs calculated, we can take a lone pair and pop it up to the bonding pair category. So now we have 3 bonding pairs and 11 lone pairs that we want to place around the atom. So I left that part for us to do in this video because it does have an additional thing that we haven't seen before when we're drawing Lewis dot structures. And that is what happens when we have an extra lone pair. So let's start this up. So we have our 3 bonding pairs checked off. We're good. We've got that done. Now we're going to go in and try to do our 11 lone pairs. And first thing you're supposed to do is look at your center atom. And chlorine right now only has 6 electrons with your 3 bonding pairs, so we need to add a lone pair to it. And that's 1 lone pair, and we've got 10 more left over. Every fluorine, if you count, only has 2 electrons, so it'll need a total of 6 electrons or 3 lone pairs. And if you'll notice, right at this moment, we've only used 10 total lone pairs. We have 1 extra. So what do you do when everything in your substance looks like it has an octet filled with bonding pairs and lone pairs, and you've got an extra lone pair? Well, the center atom will sacrifice and take that lone pair. So what I typically do is I'll take the 1 lone pair that I already have on that and move it kind of over and even turn it kind of at an angle. And then what I'll do is I'll add my second set of lone pairs off to the corner. So in this particular situation, yeah, you're not really technically adding something in kind of that north, south, east, west quadrant type situation, but this is a special one, a special situation where we have more than an octet. And this would be considered a hypervalent substance as well. So now that we have the Lewis dot structure taken care of, let's go through and try to determine our electron pair geometry. And then what we're going to try to do after that is let's figure out our molecular geometry or structure. So first thing we have to do, according to VSEPR, is figure out how many areas of high electron density there are. So we count all of the bonding pairs attached to our center atom and all the lone pairs attached to our center atom, and we sum that up to be 5. So if we go back and look at our diagram again, the number 5 here, that tells us trigonal bipyramidal. All right. So trigonal bipyramidal. And you can try to draw that if you would like to. And we can actually look at this on our Phet simulator as well. So we'll go ahead and show our lone pairs, and it says 3 bonding pairs if you remember, and 2 lone pairs, so we'll add an extra lone pair in there. And so this is the structure that you're trying to build. This is the trigonal bipyramidal for CLF3. And if you'll notice, if I look at the electron trigonal bipyramidal as electron geometry. But what is the molecular geometry? And so let's go back to our diagram again in our table, and we're going to follow along, and we know there are 2 lone pairs. So we're going to match these together. That shape is going to be what we call T shape. And again, that looks something like this. So you'll have your all of your bond angles will be traditionally 90 degrees to anything adjacent. Now, if you go along this long axis from the left to the right at the top, that's 180 degrees. But then the 2 lone pairs are kind of poking out on each side, and this gives us a molecular geometry name, again, of T shape. And so that will be our name for our molecular geometry, T-shaped. And so that is the structure or the name that we're wanting to identify here. So that's how you go through and use the VSEPR theory to move from something that's considered 2D all the way to something that then is what we consider 3D. We're going to use this 3D structure to assess some more facts about a molecule in later videos. And so stay tuned to watch those as well.